because then we can test out whether you can actually hear me or not, whether I'm clear. How's that? Hello. Nada. Hello? Better. Yes. Hello. Can you hear me? So it would be good. I know that the words that I'm saying may or may not be clear, but as you start to settle down into your seats and lower your voices, you'll understand me a little better, and that's why I'm speaking. To spread calmness and a somber atmosphere. It looks like it's worked. People are starting to calm down, and the noises remaining are just the clinking of dishes and so forth. I think that we are ready to begin. Can you all hear me? No, you can't. Well, how did you know what I was saying then? Most of the stuff will be on the screen, but if you can't hear me, it'll be a problem if you can't hear the things coming out of the speakers. How's this? Good, okay. I will speak very close to, I guess we have to use this mic. All right. So, welcome to the ACM SIGARCH IEEE TCCA Awards Ceremony at ISCA 2024. We do this every year. We have awards. We celebrate people who have accomplished things in our community, and it gets longer every year. So if you know you're getting an award, please be prompt and stick to the time. Okay. So Rajiv and I will be presenting the awards. Rajiv on behalf of SIGARCH and also on behalf of the ISCA Program Committee, and I on behalf of TCCA. So this is where we need quiet. So there have been, unfortunately, a number of people who have passed away in our community, and when that happens, we begin the ISCA Awards ceremony with eulogies for those who have passed away. Most of the folks who are eulogizing the people who have passed away have provided their presentations by video because they couldn't be here, and so we're going to have a few videos, and hopefully the sound works out. Okay. The first person we're going to, so I'm sorry for finding out this way. Robert Denard passed away, and we have a video from
Hi, this is Pradeep Bose at IBM Research. Sorry I could not be there in person.
Okay.
It is of course a distinct privilege. And
we can't hear the audio output.
Hi, this is Pradeep Bose at IBM Research. Sorry I could not be there in person. It is of course a distinct privilege and an honor to be asked to say a few words in remembering Bob Denard. Denard is of course best known for inventing DRAM and the scaling theory that is named after him. His awards and recognitions are many, as listed here. I thought, though, it would be best to watch a brief video clip honoring his life and career.
When I first joined the company in the 80s, Bob Denard was the special guy. He had invented so much of the technology, and he was the de facto leader in semiconductors at the time in IBM.
Denard grew up in rural Texas. He grew up for a while on a farm without electricity in the early 1930s. He was educated in a one-room schoolhouse. He came to Carnegie Mellon to get a PhD in electrical engineering and showed up at IBM right at the time when the microelectronics industry was coming into existence. His first contribution was in 1966 when he invented a memory device called a dynamic random access memory, the single-cell transistor. And what was important about the DRAM is it became the fundamental building block for this industry, which literally transformed the entire world.
It would be impossible to create a lot of the products that we've created through all these years, the games, the cell phones. I mean, it just wouldn't be possible.
It's just a one transistor, one capacitor. Yeah, it's so simple. It's a piece of very beautiful physics.
I think the simplicity which was clear in Bob's mind was not clear in anybody else's mind.
He made a second significant contribution, which in a sense is even more important. In 1972 and then again in 1974, he outlined what he called the scaling theory. With each generation of technology, these devices got smaller, they required less power, and the computers got more powerful. And that process led through something that's referred to as the golden era of scaling.
In my time alone, we've gone from a single transistor to tens of millions of transistors on microprocessor chips. On memory chips, we've gone from 16 bits to 64 million bits.
He was intensely curious, he was a problem solver, and those two qualities are what make the best researchers, not just at IBM, but throughout the entire computing industry. He is seen as the archetype for the best and the brightest of the world's engineers.
What I want to tell you all is that if you want to be successful, attitude is everything. You have all the knowledge you need, and you ought to be ready to have the attitude to do something with it.
The next person we will eulogize is Luis Barroso. He passed away earlier this year. He's being eulogized by Partha Ranganathan from Google. And hopefully this video works.
Partha Ranganathan, and I'm here to celebrate Luis Andre Barroso. Luis was an eminent computer scientist and a giant in the computer architecture community. He passed away on September 16th last year at 59 and leaves behind a tremendous legacy. Luis was one of the early researchers designing the first multi-core CPUs, something that today is foundational to every processor. He then joined Google, where he pioneered the design of warehouse-scale computers, designing much more energy-efficient servers and data centers. Luis's work laid the foundation of an entire hyperscale industry, and his innovations now underpin virtually all the hardware architectures that power today's internet services and cloud computing systems. Outside of architecture, Luis also worked on other influential software projects and teams, leading Google's Geo and Core software teams, eventually leading all technology coordination across all of Google's products. His work has been recognized with an incredible list of awards: ACM and AAAS Fellow, member of both the National Academies of Engineering and Arts and Sciences, and of course, the ACM IEEE Eckerd-Mauchly Award, computer architecture's most prestigious award. Beyond his core work, Luis also found ways to contribute in numerous other ways. During the pandemic, he was one of the key people who drove Bluetooth-based contact tracing, which saved tens of thousands of lives. He was a strong champion of diversity, including significant contributions in supporting the Latinx community, both inside and outside of Google. Luis was also an accomplished guitar player and also a gifted nature and wildlife photographer, passionate about preservation. I'm glad we get to honor Luis here at ISCA. I know he would have been very excited about this first ISCA in Latin America. I'm also glad to announce that we'll have a special issue of IEEE Micro magazine devoted to the past, present, and future of warehouse scale computing that will showcase the impact that Luis's work has had on our community. This special issue will come out September, October of this year, and it will be guest edited by John Hennessy, Christos Kazalakis, and Gabriel Fossau. Finally, thanks to the efforts of many members from this community, I'm also happy to announce that we'll also be instituting a new award, the ACM Luis Andre Barroso Award, to recognize researchers from historically underrepresented communities from across the world who have made fundamental contributions to computer science. But beyond all these, Luis's biggest legacy will be the profound impact he had on the people around him. Receiving the Eckerd-Mauchly Award, his acceptance speech was a masterclass in grace and humility, where he called out more of his collaborators than his own work. I was lucky to have worked with Luis for nearly 3 decades, from working with him as an intern 25 years ago, to being a co-author on the Data Center as a computer book, to continuing his work as the infrastructure computing technical lead at Google. It was a privilege working with and learning from him at every stage. This picture that you see on the screen was the very last picture I took of him when I spent a full day at his house where we made chocolate together from scratch. True to Luis, this was as much about engineering as it was about chocolate, and it's a memory I'll cherish. Luis always found a way to acknowledge and celebrate the good in people, identifying their hidden talents, but he also fully believed that he would use those superpowers to change the world for the better. And that, to me, is how we can continue to celebrate Luis, by writing the rest of his story in the years to come. Thank you.
That was very touching. The next person that we're going to honor with the eulogy is Lynn Conway. She passed away recently. Sorry if you haven't heard. We have a video from her colleague at Michigan, Valeria Bertacco.
Good afternoon, dear colleagues. I'm sorry to join you today to share the news of the passing of Lynn Conway on June 9, 2024. She was 86 years old. Most recently, Lynn Conway was a faculty emerita in my own department of computer science and engineering at the University of Michigan, and she would occasionally come to our faculty meetings, which is how I got to know her several years ago. Lynn, no matter her age, was always enthusiastic about technological innovation, always ready to discuss and brainstorm new ways to advance computing. She was a great listener and an inspirational speaker, and she always took a very positive attitude towards every discussion. She had a wide-angle perspective. She believed in change, in technology, and in hope for the future. And so it's with that spirit that I would like to take a minute today to celebrate her life with you. During her long life, Lynn Conway was a pioneer in computer architecture, in chip design, and a transgender rights activist. Her many impacts on the world will continue to reverberate for many, many years to come. In the late 70s, chip designers were reaching the limit of scalability in terms of number of transistors in a single chip. When the first microprocessor by Intel was manufactured, it had 2,300 transistors. By the late 70s, we had tens of thousands of transistors all in the same chip. And those designs were made by hand, literally, paper and pencils. And when you needed to debug, you would erase a portion of your drawings and then draw it over again. Right at the height of this scaling crisis, Lynn Conway invented the lambda rules and algorithms so that computers could support the design of chips. And with that, she launched what we call today the VLSI revolution. My entire field of electronic design automation, thousands of researchers, multi-billion-dollar industry would not exist if it weren't for Lynn. Those of you who are baby boomers may remember reading and studying her VLSI Mick Conway book. But this is not all. Lynn was also internationally recognized for her advocacy on transgender rights. She was one of the first Americans to undergo modern gender transition, and she faced a great deal of discrimination. Indeed, she was fired in 1968 when she decided to transition. She conducted her research work while keeping a very low profile for several decades. And then finally, in 2012, she decided to tell her story in a special edition of IEEE Circuit. And then she went on to develop a robust catalog of online resources and advice about gender identity and transition. Lee was also an advisor to my own application-driven architecture research center. She would regularly come to our annual symposia. I instituted the Lynn Conway Research Award for students, which would recognize a student with the most impactful research within the center. And Lynn would come to our annual symposia, give the award to the students, and give them a signed copy of her book. I would say the best memory of Lynn that I have in my mind is her sitting at dinners with the students, all intensely engaged in discussion about the future of technology and the future of computing. Lynn is a colleague, an innovator, an inspiring mind, and she opened the door of VLSI for all of us. May she rest in peace. And I wish all of you a great ISCA 2024.
So we have one more eulogy. I apologize if this is how you're hearing about it. Arvind passed away very recently. We're going to have Joel Emmer come up representing his colleagues and Derek Chu representing the students.
Thank you, Daniel. Yeah, we're very sad to share the recent and sudden passing of Professor Arvind. Arvind, as many of you know, it was just Arvind, like Madonna, Cher, or Sting. He's been a giant in multiple distinct domains: computer architecture, data flow, functional languages, and EDA. The computer architecture domain, whenever you talk about today the data flow of an architecture, you could be thinking about Arvind, who provided the seminal contributions in that area. In computer architecture as well, beyond his contributions in data flow architectures, he also made significant contributions in parallel computing, memory models, and acceleration. Collaborating with Arvind, either as a student or as a colleague, changed one's life. He usually did not follow the current vogue research trends of the day, but instead sought the underlying truths and a deep elegance, even beauty, in technical work. For example, in the transition from sequential to parallel programming, he was sort of aggrieved by what he perceived as the ad hoc descriptions of parallel programming constructs, and therefore worked hard to gain deeper insights, largely through formal semantics. That pursuit of deep understanding meant that everybody working with Arvind heard, quote, "I don't understand," quote, 1,000 times. That could be quite frustrating, but forced us to distill our ideas down to their fundamental core. During those discussions, it was often Arvind who came up with an elegant, concise articulation that captured the essence of the problem.
Arvind approached teaching with similar earnestness. Every lecture was meticulously prepared, rehearsed, and treated like a performance targeted to the brightest young minds who would likely stump you with the hardest possible questions, testing your depth of understanding. He would often spend days prepping for an hour lecture. I was his TA, so I know this, that he had given so many times before, painstakingly going over each point with his co-instructors and TAs. Although he was very serious professionally and always sought out academic rigor, he took huge joy in life, as seen in his wide smile and his gregarious laugh. Arvind was a real family man. His research group was his extended family. His wife, Gita, would often take their sons to his office at MIT when they were young, as much to see the grad students as to see Arvind. He and Gita would often invite the group to their house, mixing with their other friends, family, neighbors, and whoever might be visiting them at the time. For everyone whose life he touched and felt his deep kindness, we will miss him dearly.
Thank you, Derek and Joel. All right, now we're going to have, it's not Babak, it's going to be Rajiv. He's going to present the ACM Fellows.
I just wanted to thank Pradeep and Valeria, Partha, Joel, and Derek for those touching celebrations of our colleagues. Next, I'm going to recognize people from our community that got elevated to ACM Fellow last year. If you're here in the audience, please rise. The ACM Fellows from the class of 2023, Haibo Chen, Pradeep Dubey, H.T. Kung, Anand Raghunathan, Stefan Saroyu, and Emmett Mitchell. Please give them all a hand.
Congratulations to the ACM Fellows. We also want to celebrate the newly elevated IEEE Fellows in this year's class. The IEEE Fellow class of 2024 from our community is Rakesh Kumar from UIUC, Xiaoying Ji, Axel Janch, Alex Jones, Hesun Kim, Ben Lee, Dimitrios Nikolopoulos, Sudeep Pasricha, and Carlos Sankaralingam. If you're here, rise, please. Congratulations to the ACM and the IEEE Fellows. Right. Next is the ACM SIGARCH IEEE-CS TCCA Outstanding Dissertation Award that we present at ISCA. This award recognizes an excellent thesis research done by doctoral candidates in computer architecture. The committee was Murli Anavaram, Ritu Das, Christina Demetriou, Stefanos Kaxiris, Yasko Eckert, and Caroline Trippel. So they went through and did a lot of work and found us some winners. Honorable mention, she couldn't be here with us today, but let's give a round of applause to Poulami Das from Georgia Tech. The citation for her award is, or the title of her dissertation is Software and Architecture Techniques for Improving Fidelity of Emerging Quantum Computers. And her advisor is here, and congratulations to him for leading her to that dissertation. And the winner of the dissertation award is Tanvir Ahmed Khan from Michigan. Rescuing data center processors. His advisor is also here, Barish right there. Congratulations to you. And Poulami's advisor is Moin Qureshi. I don't know, do we not have that on the slide? Okay. So they're not, Tanvir couldn't make it, but we're going to send them their awards through the mail. Congratulations to them. Next, we have the 2024 IEEE-CS TCCA Young Computer Architect Award. So this award recognizes outstanding research contributions by an individual in the field of computer architecture. It's open to anyone who's completed their PhD within the last 6 years or with possible extension due to unusual circumstances. This year, we were very pleased to have 2 winners of the YCA Award, the Young Computer Architect Award. The committee was Alberto Ross, Christiana, who's the chair, Christiana Silvano, and Gilles Poulami. The first winner, there's no particular ordering, but they both won the award, is Mengjia Yan from MIT. I'd like to invite Mengjia. So Mengjia is going to come and give us a few remarks.
Thanks a lot. It's really a great pleasure to get this award. At this moment, I really want to appreciate a lot of people who have been witness and helped me so much along the path, especially my advisor, Joseph Trellis. He kind of guided me into this domain when I was barely know anything about research. So now, as I'm a faculty, I realized that how patient he was with me when I was really very naive. And also, I really to appreciate Joe Emmer and Srini Devadas for writing the recommendation letters for me. And it was really a big fortune, a pleasure to work with them as colleagues. And they kind of significantly influenced my taste of research, especially Joe's elegant taxonomy and abstraction. And also, it's a great privilege to work with them, co-teach with them, and they uplifting my understanding of how teach should be look like. Besides, I really want to thank a lot of people who have influenced my research along the path. For example, Chris Fletcher, when he joined UIUC, I had the time to have a lot of in-depth discussion with him about how security should be studied in the computer architecture community. And he is really a great role model for me because of his passion for research and all the positive vibes he sent around his students. I also really want to thank my lab mates at UIUC. There are a lot of them. I got a lot of help from them, especially Dimitri and Berghoff. We cried for paper rejections many times, and I'm really happy that Dimitri could, also became faculty at CMU so that we can suffer more together. And after I joined MIT, I also got really lucky to work with Toma Bosha and a professor from Princeton, Sharad Malik. They kind of exposed me to new research areas, so you know that I literally work on hardware security. Nowadays, helped with getting help with them, I'm learning a lot from programming languages and formal methods, and I just feel like doing research, the most fun part of doing research is learning new things. In addition to that, I also want to mention that Arvind, we are memorizing him today. I was very fortunate that even though he was super busy and having health issues in his last few years, he was still willing to spend a lot of time giving me lectures and my students lectures on lambda calculus. That shows how dedicated he is for supporting junior faculty and just enjoy research by itself. Meanwhile, I also want to thank all the faculty members at MIT for all the support they gave to me in the last 4 years, especially Vivian Z. Thanks a lot for all the weekly therapy sessions to go through all the things with me. And Martin, Daniel, Srini, Joe, Arvind, thanks a lot for making me feel I really belong to MIT, that place. And I'm very fortunate to have my students, Peter, who tolerate my immature mentorship. He's my first student, so that is somehow unavoidable. And Yuhan for fearlessly exploring new areas with me, and Joseph for introducing this just unbelievable vibe in my group, and Shixing, Vincent, and Daniel, Jules for all the trust in me, while I was not clearly whether I will be doing anything successful or not. Finally, there's a lot of collaborators. I will not be able to, I must have missed someone. I thank Sudanva, Adam Chpala, and my postdoc who will join USC as an assistant professor. Thanks a lot for all the collaborations and the inspirational discussions. Finally, thanks all my family and my partner for the long-term support, unconditional support, and all the tolerance for my ignorance while I work on the research papers. Thanks a lot.
We have a plaque for her. Congratulations, Mengjia. Our next TCCA Young Computer Architect Award winner is Prashant Nair. So he has a few remarks for us.
Thank you, Daniel. I'm deeply honored to receive the Young Architect Award. I must say that I owe this award to DRAM and the challenge it presents today. DRAM scaling has enabled a lot of critical applications, data-intensive applications, but today it faces several critical security and reliability issues. Over the years, a lot of open research problems have been solved by several researchers, and I'm glad that I was one of those few people who also took a few stabs at this problem. Now, this award would not have been possible without my collaborators at UBC, at IBM, and at Georgia Tech. I want to particularly thank Tor, Mayeshko, Karthik, Pradeep, Alper, Bulant, Gururaj, Sumit, Poulami, Sokin, and Divya for their collaboration. I'm incredibly thankful to my students, Adnan should be here, Meng, Junghyun, Yasaman, and Mushahid, for being so passionate about doing their PhD and their research. I'm also deeply grateful to my advisor, Moin Qureshi, who taught me how to conduct research and how to do good research and write good papers. His importance on looking at simple, novel solutions influenced me a lot. It was very clear that he is a very good advisor, and he continues to be a very good advisor. And like many here, I do not come from an academic background or an academic family. In fact, no one in my family holds an advanced degree. Despite our financial challenges, my parents continue to support my learning and my education. It is often said that life is the best teacher. On that front, my brother showed me what it is to have a life more than work, right? To truly care for someone. My closest friends, Santosh, Darshan, Amar, Melroy, and Balaji, taught me the importance of being there for each other. And my wife, Latasha, has shown me what unconditional love means. I cannot thank her enough for tolerating me for the last 5 years and supporting my career. The kind of sacrifices she has made, I can only imagine how tough that would be. So thank you. And frankly, if the roles were reversed, I'm not sure if I could do it. So thank you all for doing this. I would like to especially thank a lot of members of this community who've helped me grow. So thank you again.
Great. Congratulations to those winners. Rajiv? The next item will be the Maurice Wilkes Award.
All right, so next up is the 2024 SIGARCH Maurice Wilkes Award. This is an award that recognizes an outstanding contribution to computer architecture made by an individual who is relatively mid-career, and what that means is, having started your career within the last 20 years. The selection was done by a committee that was chaired by Norm Jupi, also included Natalie Enright Jerger and Chris Kazarakis. So without further ado, let me invite on stage the winner this year for her contributions to in-memory computing, Reetuparna Das of University of Michigan.
Hello, everyone. I feel very fortunate and grateful to receive this award because I know there are many other individuals who deserve it. So let me tell you my view of in-memory computing a bit. So here I'm showing near memory computing and in memory. So when the logic is outside the memory arrays, that, according to me, is near memory. The logic could be anywhere, but the data has to be read out and then computation happens. That was the first wave of PIM. What we and others proposed was, without reading the data out, how can we morph memory arrays into compute units by modifying the peripherals and sharing the charge on bit lines? So that was in-memory computing. Let's see how this technology can be very powerful. So here I'm showing you an old Xeon processor with 45 megabytes of last level cache. Cache is not a monolithic structure. If we dig deeper, it consists of thousands of arrays. And what our technology did was that it transformed these thousands of arrays into bit line vector units. So we could transform the cache into over 1 million bit serial ALUs, which can be used for AI or any other data parallel application. It could support several different operations, all kinds of precision, and it was configurable. And since we're doing data in place computation within these very tiny arrays, we could do it fast too, at a 2.5 gigahertz. That was in 2018. Now we have processors with even larger V-caches, and so this technology can be even more powerful. 7 years fast forward, in SRAM computing is a very prominent research area till now in both architecture and circuits, and it gives me a lot of joy to see that momentum in the community. Compute cache remains on the bucket list of promising ideas of CPU processors. We worked very hard with Intel to transfer it, but maybe its time will come. Multiple startups are commercializing in SRAM computing for edge AI. So that's where we are today. I'm hopeful for the future too. Parting thoughts. And this is really a message to the next generation of students and researchers. It's okay to have crazy ideas. This is the review we got for compute cache. The strength, it seems crazy. The weakness, it seems a bit crazy. Yeah. So, think of out-of-box things and see where it goes, right? And it's totally okay. It's okay to have rejections. If I count the number of proposals which got rejected, I won't be writing the next one. But don't let that get to you. Same with paper rejections. I think compute cache also got rejected 3 times, probably. So, it's okay. And that shouldn't let you down. You should just use it as a stepping stone, believe in yourself and your ideas, and move forward. The third message is, please be kind and positive to your fellow researchers. I have heard many things over my career, including women brains are smaller, I got my job because I'm someone's wife, and other things. And you're saying this to a human being with feelings. So be kind and positive. You never know how it will affect someone else. And finally, never say never. Give it a shot, give it a try, don't give up, right? So another example of never say never for me is when we started collaboration with Michigan medicine physicians, they gave us a blue sky problem. Can you do intraoperatively sequencing while doing surgery from tissue to diagnosis is within half an hour? This seemed impossible because now it takes weeks to send it out and bring it back in. For this, we set up a wet lab, learned sequencing, microbiology, and I had an amazing postdoc who kind of, did it all, and we could actually achieve that. So follow your ideas till the very end. Finally, I would really like to thank the amazing people who have made this possible, to my awesome students, starting with Shaizeen Aga and Arun Balasubramaniam, Daichi Fujiki, Charlie Eckert, and Zhaowei Wang, who worked with me on in-memory computing, as well as all these wonderful people. A shout out to Jack Warden also, who was my postdoc, our postdoc who did work on precision health. And I would have heartfelt thanks to my amazing collaborators, starting with Chita Das, who was my advisor and who introduced me to the world of computer architecture. Satish Narayanasamy and David Blau, who worked with me on in-memory computing, and my mentors, Onur Mutlu, collaborators Scott Malki, Ravi Iyer, Todd Austin, Valeria Batako, and Dennis Sylvester. They have been simply amazing researchers to work with. Finally, I would like to thank my family, my dad, who is no longer with us, but showed me how to dream and how to go beyond conventional norms and cultural norms, my mother, and my husband, who is here with me, and my daughter, Dia, who is still to this day is my inspiration. Thank you.
Congratulations to Ritu. The next thing is going to be the influential paper award. Do you want to do this or? I mean, influential paper award. So, all right. So the next item is the ACM SIGARCH IEEE-CS TCCA ISCA Influential Paper Award. We changed the process this year. I went over it yesterday in the business meeting. If you had a chance to attend the business meeting, it's a new process. To summarize, better process, more in line with what the other conferences do, reasonable committee and so forth. The committee this year was Fred Chung, Haesoon Kim, Lisa Xu, Nalian Wright-Jerger, and Murli Anavaram. The 2024 ISCA Influential Paper Award goes to the paper Exploiting ILP, TLP, and DLP with the Polymorphous TRIPS Architecture by Sankaralingam, Ramadass, Nagarajan, Haiming Liu, Changkyu Kim, Jaehyuk Hu, Doug Berger, Steve Keckler, and Chuck Moore. So, congratulations to them. Unfortunately, the authors couldn't be here, but they sent a video that will hopefully play.
Greetings to ISCA in Buenos Aires. Karu and I are proud to represent our co-authors for this award presentation. We regret not being able to be at the conference in person, but we and our co-authors are delighted to accept the ISCA Influential Paper Award. We are grateful to the selection committee and the entire ISCA community for the recognition of our work. The premise for this paper stemmed from the observation that different types of proposed processing units were best suited for different granularities of parallelism. We hypothesized that hardware polymorphism across different architecture structures would enable a single architecture to span a wider range of types of parallelism. While one approach would synthesize larger effective cores from smaller cores, in the TRIPS project, we took the approach of building a powerful core that could be partitioned into smaller units suited to fine-grained parallelism. We designed the TRIPS architecture and implemented it in chips and systems as shown in the photographs on the right. The architecture itself included two large processors, each consisting of a 16-tile CGRA connected via an operand network. The processor employed an explicit datacraft execution model with block atomic speculation and supported 16-wide execution with up to 4 threads per processor. The memory system included a 4-tile distributed L1 cache and a 16-tile distributed NUCA L2 cache. Polymorphism enables multiple types of parallelism using a common data graph computation expression. The operand network implements a programmable network, while the memory system supports caching, scratch pads, and partitioning. We employed a compiler to map graphs to this architecture.
Now we take a look back at two broad themes of the paper. First, did all forms of parallelism turn out to be important? The answer is resoundingly yes. ILP, single-thread performance, has continued to be important. When we wrote the paper, we were still seeing doubling of performance every 18 months. Over the past decade or so, this has slowed down quite a bit, but to about 6% per year. For TLP, it's bifurcated in two ways. We now see CPUs with core counts between 32 to 128 and 2 to 8 threads per core. GPUs, on the other hand, employ massive multithreading to get a version of a 1,000-way TLP. Data-level parallelism has exploded in importance. This thing called deep learning happened. There's a lot of domain-specific architectures. On the technical side, we've seen vector extensions, tensor accelerators, and dedicated DL accelerators as well. Typically, these all imply a form of graph-based execution that we introduced in the TRIPS architecture. Looking at polymorphism, did it turn out to be important? It's nuanced. On the compute side, specialization has been the preferred path. Part of it is because compute units are fairly cheap. And how has this shown up? We see CPUs queues that are specialized for a blend of ILP and TLP. GPUs have various specialized units for deep learning and ray tracing, and accelerator blocks abound in mobile SoCs. On the memory system, on the other hand, polymorphism is widespread. The reason is the converse. RAM is very expensive and you can't afford to pull different types of RAMs for different behaviors. Instead, we see SRAMs configured as a cache or a scratchpad, and it's programmable and configurable in different ways for different cache management policies as well. So that's what we wanted to share about our paper. Again, we're very thankful for the award. Enjoy the lunch and the rest of the conference.
Great bunch of guys. Okay. The next item will be the ISCA Best Paper Award. I invite Sanjay to come present that.
So this award, the Best Paper Award, was just started a couple of years ago, and we're continuing the tradition. The Best Paper Award process consisted of nominations from the program committee and also input from the PC reviewers through this process. The selection itself was done after presentation of the awards during the Best Paper Award session, and by us as program chairs, as well as by John Carter as the industry track chair. So congratulations go out to all of the nominees. Thank you for your excellent presentations during the Best Paper session. The award goes out to Constable, improving performance and power efficiency by safely eliminating load execution. If the authors could come up. So last year we had some distinguished artifact awards, and we're continuing that as well. This year, the Artifact Awards Committee decided on 4 artifacts as rising above and beyond the others in terms of really having a complete package in terms of the artifact. And so the Artifact Awards go out to, and before I actually put this up, I'd like all of you to come up, all papers at the same time, just to speed up the process. So the authors who are present, please do come up. This goes out to 4 papers: Tetris, a compilation framework for VQA applications in quantum computing; FireAxe, partitioned FPGA accelerated simulation of large-scale RTL designs; Da Capo, accelerating continuous learning in autonomous systems for video analytics; and the Data Flow Abstract Machine Simulator Framework. Authors who are here. I see one set of authors. Anybody else here? Second? Okay. Stay up. Is Blue saying?
All right, on to, I think, our penultimate award for the afternoon. This is the 2024 ACM SIGARCH Alan D. Berenbaum Distinguished Service Award. Alan Berenbaum was the inaugural winner of the SIGARCH Service Award. After his passing a few years back, it was renamed in his honor. Alan was a pioneer, instituted a number of great best practices. He instituted the Maurice Wilkes Award, worked hard on inclusivity, got the ISCA proceedings into the ACM Digital Library, and held a number of ACM SIGARCH roles. So in terms of the selection process, this was done with a committee that included Gabe Lowe, Per Stenstrom, and Catherine McKinley as chair. And our awardee this year, and please give me a second to read the citation. The award goes to Timothy Pinkston of the University of Southern California for decades of exemplary research service spanning computer architecture and the wider research community via his leadership at NSF, ACM, and broadening participation. Timothy.
I'm old school. Does this work? Can you hear me? Can I? Hello? Okay, good. Thank you, Rajiv. I am grateful to the committee for selecting me from among many highly deserving nominees this year. I am both honored and humbled to receive this award. I walk in the footsteps of many giants who have preceded me, starting from my former advisor, PhD advisor, Mike Flynn, who received this award back in 2016 for, among other things, founding SIGARCH and founding TCCA over 50 years ago. And I continue to walk in the footsteps of others, many others who have also been recognized for their outstanding service to the computer architecture community, including people such as Mark Hill, David Wood, Catherine McKinley, Per Stenstrom, and Margaret Martinosi, just to name a few, with Margaret also recently receiving the ACM Francis E. Allen Award for her outstanding mentoring. Can we give her a big round of applause? So many countless others in our computing community have likewise contributed excellent service who haven't yet received any recognition for it with an award, but for whom their service, no doubt, has been rewarding and gratifying to them. So I wish to accept this award in part on their behalves as well. My main takeaway message for everyone here is simply the following. It is a privilege and an honor, and in some ways a responsibility, to volunteer service to our technical community, whether through service in leadership on conference and workshop committees, organizing committees, or through providing reviews of papers and research proposals for funding, or through volunteering your service as a mentor to our more junior colleagues and students, or even in outreaching to persons from diverse backgrounds who are underrepresented in computing, to broaden participation in computing. These and other acts of service all help to keep our computer architecture field vibrant and thriving. May you all be inspired, and I look forward to seeing and benefiting from the outstanding service each of you will be providing in the future. Thank you again.
Congratulations, Timothy. That was awesome. The next item is the 2024 ACM IEEE-CS Eckert-Mockley Award. Will be presented by Steve Reinhardt.
Hi. Hello. It's my honor and privilege to have been the chair of the 2024 Eckert-Mockley Selection Committee. And let's see here. I think the award itself needs no introduction. The highest technical award in our field, recognizing contribution to the field of computer architecture. I would like to thank and acknowledge all of my fellow committee members, Steve Keckler, David Brooks, Lizzie John, Christina Savano, and Tim Sherwood. And I'd like to say that we met and went over all of the nominees very carefully, and rank ordered them, and there was a unanimous agreement of the top candidate stood out head and shoulders above everyone else. And in fact, we had a brief moment of panic saying, hasn't he already won this award? Shouldn't he have won it by now? But we double checked, and he had not. So it's my great pleasure to announce this year's award winner, Professor Wenmei Wu. And of course, our biggest challenge was summarizing Wenmei's contributions in a single sentence, but this is what we came up with. For seminal contributions to architectures, compilers, and adoption of multiple generations of processors, including superscalar, VLIW, and GPUs. So congratulations, Wenmei.
Sound? No. Okay. Oh, good. That doesn't look good. Yeah, that's what. One more time. Okay. It's not. Sí, lo que sí me interesa. Great. No me parece el mouse.
Hello? Hello? Can you hear me? Great. Thank you, Steve, for the amazing, wonderful introduction. I have to apologize to Steve because when he called and tried to tell me about the award, I thought he was a spammer. so I actually rejected this talk. I want to start by recognizing those who received the award ahead of me. And this is a list of giants. As Sir Isaac Newton would say, these are the giants who lend their shoulders to us so that we can see farther. But in computer architecture community, we should perhaps say, these are the giants who let us stand on their shoulders so that we can accelerate the computer systems better. And for many of them are here today, and I already saw several of them already. So Joel is here, Mateo, and Uri, and Mark, and Margaret, and Conley. So it's my true honor to be able to come after you. So what is parallelism? There are many, many definitions of parallelism, but a simple definition to me is that parallelism is the number of operations in a task and the level of flexibility in their execute order. And that flexibility is truly what's fueling a lot of our optimizations today. In many ways, that has been saving us since the end of the dinar scaling, and we just memorized dinar earlier. The research that I have been involved in my career started in 1984. I started grad school in 1983, and I took a computer architecture course from Yale Pat. And Yale taught me two important things in that class. It has nothing to do with computer architecture. It actually taught, the two things are, one, I'm far, far away from being a international level researcher. So it's way far away. And the second one is, all of us can actually have a path to get there if we really wanted it. And those are the two things that stay with me forever. Of course, we learned a lot of computer architecture work. And three of the most significant things I learned in that computer architecture course was, one, the data flow work by Jack Dennis and Arvin. And the second one is Thomas Sulo's work from IBM 36091. And the third one is actually Mike Flynn's, the classification of the parallel architectures. So we started the work in 1984 when I joined Yale's group. And I'll come back to 1984 a little bit later. It's a really, really important year for me personally. But we were actually significantly or substantially motivated by Joe Emmer's work. Sorry, Joe, I should have also mentioned you as the previous the Edgar Markley Award winner here today as well. And we actually met in, I believe, in Hudson, Illinois, but Massachusetts, when I was an intern at Digital Equipment Corporation. And I already read Joe's paper on the VAX IPC numbers in ISCA. And, but I got a whole lot more insights by just chatting with Joe that summer. And then we actually also had a lot of influence from Jack Dennis and Arvin on their data flow work. So we were scratching our head trying to figure out how we can apply the data flow principles to accelerating the computer implementation. So in 1984, we eventually figured out a model that is depicted here. And that was the paper that later was published in Micro 1985. Just to set the record straight, Mike Shebenow and I actually had access to an Apple IIc. And we drew a very nice professional looking picture, but Yale didn't like it. So he insisted that his hand-drawn picture is so much better than ours, that he absolutely wanted this picture. So for those of you who have been laughing at that picture, I was not responsible for this particular one. We actually had to flesh out the work of the lower half of that picture in the next 4 papers. And along the way, there were two very, very important concurrent work. One is by Jim Smith and Andy Plashkin on the precise interrupt handling in pipeline processors. We substantially improved the work for out-of-order execution, and I'll mention the key observations we made. And the second one is actually the Guri Sohi and Vanessa Yapin's work in 1997 on the instruction issue logic. And I personally believe that that piece of work was very, very influential and very important in so many ways. So we would have to wait for quite a few more years before Ye and Pat did the work on branch prediction to finish the upper part of that vision. So by that time, the HPA vision is complete. There are a few things that we learned along the way that I would like to share, especially with our younger attendees here today. The first one is that the key insight of this work, 4 years of work, thesis, many papers, if I look back and look for one key insight, the key insight is we changed the register file to a mapping mechanism so that we can solve the precise interrupt problem for out-of-order execution in a clean way. And eventually, when I taught the course in architecture course, again, it's very important to teach these courses. I taught a student called Andy Glue who liked that idea, and he brought the idea to Intel, the P6 group. I think Conrad is here, and he probably still remembers some of that history. And he built the P6 register file as a mapping mechanism, and he named that register file as RAT. It's a register alias table, and I actually gave that structure that name in my thesis because it was such a bad structure to debug. So I always call it a rat. And then we figure out how to give it a nice name to legitimize the name. So that's only one key insight after publishing so many papers, right? So looking back, I wish that we had published fewer papers, but probably even deeper insight. And the second one is that the discussion with the Digital Equipment Corporation, many of you who are young here probably don't even remember that name, but the Digital Equipment Corporation was a truly, truly innovative company, and so many of the Intel, the architects and so on, and HP architects came from that generation. And we had great the discussions with the digital engineering team, and especially Fernando and Steve and Nii and the Mario and Bob. One thing that I learned as a grad student is that sometimes the senior engineers can be a little bit heavy-handed. So I remember during one of the meetings, Fernando said something about what I did, and I was so angry with him that I walked out of the room. And I was a young grad student, and I feel that this one is, I was calling him a name that I'm not going to repeat here. And Yale calmed me down and said, if you cannot take criticism from someone like Fernando, you don't have a future in computer architecture. And I walked back to the room, and I apologized to him, and he taught me a whole lot more things after that. The second thing, the second part is that talking to some of the veteran architects who actually had their hands on real machines, either design or analyzing the machines, was incredibly helpful. And Joe being one, and Nick Tredenik, and Rich Belgard, these are the people who, who, if you sit down with them and you ask the right questions, you get to understand the soul of these machines so much better. The third one is, as a grad student, I never fully understood this. I always thought about great ideas and so on. But the truth of the matter is, after 40 years, nothing is new under the sun. Nothing is completely new, maybe. And in fact, one of the most frequent feedback I got when I was working on HPS and later on Impact, is that this is something that IBM probably has done a while back. And it turned out that most of them are true. On the other hand, I really believe at this point, that adapting old ideas or old solutions to enable new applications and new systems and new technology moves the world forward. And I think that's really, after 40 years, I believe that's the real job of a computer architecture researcher. We're not here necessarily to give the world brand new things every day. We're here to help the world move forward. The next one is, be thick-skinned, okay? And I heard this, a couple times already. During one of my interview seminars, one of the researchers I highly, highly respect came to me and said, nobody will ever build a real processor based on what you just presented, HPS. I was talking. And thanks to the P6 team who did a heavy lifting and built a P6 processor based on these concepts, I was able to get a real apology from this person about 10 years later. And the true privilege of being thick-skinned is that now whenever I see Mark, whenever I see him today, I get to remind him what he said in 1987. And he takes it so well. Okay. So in 1987, I started a career at the University of Illinois. And I feel deeply, because I was analyzing all the compiler code for HPS, and I realized that there was a huge gap between what we wanted in the code, and I was actually doing a lot of hand coding, right, to figure out what the deficiencies are. So I ended up starting to build a compiler, and I thought that we were going to be done in 2 years. It only took about 14 years. And we published about 15, what we call the defining papers about the technology. But in my mind, what we really were doing was we're really building the compiler infrastructure that we wanted to be able to extract the parallelism or create more parallelism through these transformations. And looking back, we probably still publish too many papers. And so one of the central messages is let's publish fewer papers. And think more deeply and publish fewer papers unless your student really insists that they need the papers to find a job. And so there are a few lessons that I learned from the Impact days. One is building and demonstrating a compiler is greater than 90% engineering work. And we were struggling with debugging. We're doing daily builds. We're doing the regression test, and we're debugging all the time. Rick Hank would tell you he was the registry allocator person. He's currently at Google, still responsible for their compiler code generation. And he will tell you that he gets blamed 95% of the time, not because of his fault. It's just that everything manifests themselves in the code generator after the code generator spits out the code. But then, I think there are two things important about this. One is if your goal is to move the world forward, having that kind of effort is important when it comes to moving the technology into real use. Later on, when we transfer technology to Intel compiler, GNU compiler, and eventually NVIDIA compiler, Roger Brinkman and Brian Dietrich are still responsible for the NVCC. And then, it's all effective in training the next generation leaders. And I believe I heard similar things from the previous recipients about the importance of these engineering efforts. And the second one is the collaboration with the HP and Intel engineering teams was incredibly important. And we learned so many important constraints and the subtle problems from that team. And the third one is, learning from visionary researchers is incredibly important. I still remember taking a walk across the Cambridge campus with Mike Flynn and during the Michael in Cambridge. And that afternoon, I learned so much insight. And there was a dinner with Arvind in Barcelona, and Mateo was hosting that dinner in Barcelona. And I only heard "I don't understand" from Arvind 3 times that evening. Okay, remember that "I don't understand" thing? But at the end of the dinner, I figured out how to explain something so much better by just talking to him. Okay? And a new paradigm really needs to jump over a pretty high bar, even if it's just recompilation. I had to spend more than 10 years of my life to learn that this is the case. It doesn't matter. As long as you're not multiple times better than the state of the art, no matter how good the technology is, it's not going to make it. Itanian did not. And then, that brings us to kind of the GPU computing era. From 2001 to 2006, I was searching for some reasonable solution, as we know the Moore's Law was kind of ending. We're still saying Moore's Law is ending, and some of you will say yes, some of you will say no. I'm not going to here to debate that one. And but there was a lot of great programs, sponsored by SRC. 2 of the we met in one of these programs, and we were talking to so many people, and we were trying to figure out, right, what's the best way to move the multi-core, the pathway forward. So in 2006, David Kirk came to Illinois, and we had dinner together, again, talking to visionary people, right? And then, after a few glasses of wine, he said, Wenmei, why don't you just, forget about the CPU multi-core? We have this thing coming out, and this thing really needs to have a lot more research to, to be able to be real. And said, David, you're in California, I'm in Illinois, and you're asking me to teach a parallel processing programming course of this piece of hardware, and then you're going to get me, my students, to do research on this thing while you are enjoying your California weather. That's not fair. So David said, I can correct that. So Jensen Huang gave him his private jet, and he flew to Illinois every week on Monday, and returned to actually Colorado, not even California, on Thursdays. And that was 15 weeks of real collaboration, and we took it, we got it off the ground. So G80 started with 8 of these SMs, streaming multiprocessors. In my opinion, that's closer to the CPU core. And then each core can support up to 780 threads, which is about 24 orbs, and that's closer to a CPU thread. So, we have 196 of these equivalent threads that we can work with, and said, okay, with that level of parallelism, I can probably do something about it. So we work on, the biggest trouble with this particular piece of technology it's not recompilation, okay? There's virtually no infrastructure, no applications. So we had to do a few things. One is co-optimization. We wrote a paper about it. The reviewers said there's nothing new in this paper, and there's, all these techniques are known techniques. You're just applying to a new piece of hardware. We say, yeah, that's the point. And so, I think the citation kind of speaks for itself. So I would love to talk to the reviewer again at this point. And there are many other things, but I think one of the interesting experience I would like to share is building a large system based on GPUs. In 2013, we deployed the Blue Water system with 434 GPUs, but I would like to just kind of talk about that just a little bit more. And we wrote a textbook about this, and again, one of the things that we really learned is that unless you can write a textbook about the technology, you really don't understand it. And I had to talk to so many people about some of the details to be able to figure out that I actually didn't understand something. Okay, quickly, a few lessons learned. One is be thick-skinned, okay? This is the second time I talk about being thick-skinned. During the, there was a little bit of a twist of the Blue Waters project. We originally proposed this machine as an IBM power machine, but IBM pulled out towards the end of the planning cycle, and we had to go with Cray, and then we proposed to add GPUs to be able to get to the level of flops that we were targeting. During the review, I presented the GPU plan, and I can feel that the panel was lining up like a firing squad. Okay, I saw all the lights coming my way, and I said, so I had a bad feeling about it. So after the panel, there was a summary, and the summary was about the GPU section. Is that the proposed 3,000 GPUs in Blue Water is maybe, to say the least, risky. And then verbally they said maybe even irresponsible. And these are supercomputing center directors who look at our plan and have very serious doubts about whether this thing is going to be the biggest embarrassment of NSF history down the road, right? But luck sometimes strikes. Irene Quarters, who took over the whole program from Steve Minchin, and she believed that we can pull it off. So she actually worked the system, allow us to have the 3,000 GPUs in there. 4 years later, 3 years later, maybe, after the acceptance test, we actually had 4 science teams working on real deployment level application, and I was responsible for that whole acceptance test. And so, after the review, the same panel came out and said, "Oh, this was truly a great idea. How come you only have 3,000 GPUs in there?" And so they added another, 1,000 GPUs. And so, I was looking at the same panelists. They were all smiling. They were all claiming credit, for what they recommended last time, even though they don't remember exactly what they said. But that's good. That's good. We all share glory. We all share credit. But the real credit belongs to the Cray team, the NVIDIA team, and the science teams who worked so hard, right, to get the results. And the third one is, teaching is so important for research. And many of us know that we don't get credit for teaching at the universities, right? But I took a class, a network analysis class from Dick Karp when I was at Berkeley. And he truly taught us that as he teach, we can see that he was processing, he was refining some of the things he was thinking about the network analysis algorithms. And he and Tarjan later became legendary, right, in that whole field. So, there's no alternative but teaching something so that you can truly understand what you're trying to do. And writing a textbook, by the way, is truly a bad idea if you try to get a little bit more income for yourself or your family. I calculated the dollar per hour for writing that textbook is actually less than $1, okay? So, even though we sold 25,000, 30,000 copies, but, if you look at the number of hours, it's truly a bad idea. But it really is so important for the movement. We would not have been able to bring the science teams and some of the Google and Facebook teams with us if we didn't have the time. So this is the review slide I presented at the Blue Waters acceptance review panel. And we jump over the bar because adding a GPU, which is Keckler, by the way, it's a very modest GPU, Keckler, into the system, we improve the system performance by about 4 to 5 times. But if you look at socket by socket, the 2-socket performance with 2 sockets of CPU was over 2 times. That was good enough. And we learned two important things. One is all these numbers are not 100 times speed up that we were hoping to get. These numbers reflected the memory bandwidth ratio between the GPU and the CPU. That triggered a lot of the HBM work later on, right? And the second one is, if you look at these numbers, we actually were also limited by network bandwidth. So that was the secondary limitation, and it makes sense for NVIDIA to acquire a networking company called Mellanox later on. Okay, quickly, in the future. So what would I recommend some of our younger colleagues to look at? Many of you were at the keynote this morning. Sridhar talked about something very important, and he was talking about retrieval augmented generative AI. And that's one of the applications we are seeing at NVIDIA, which is growing so fast and so important for the future of inference. And there are 6 categories of these applications: search, and data analytics, and for the financial industry, graph analytics and graph neural networks, and so on. And all these applications are running several orders of magnitude off from the theoretical limits that they should be able to run on either the CPUs or GPUs, okay? So why is that? The fundamental problem is we computer architects have long accepted an assumption that the compute domain and the storage domain, network domain, should be separate. And in the memory domain and the compute domain, we have data structures and we have code. But then we have the network, we have the storage, and these things are opaque to the applications unless through the memory mapped I/O files. But the memory mapped files, as we all know, is a no-go for performance. So what do? In the past 20 years, what we found out was that we used to have significant amount of time in the application code, significant amount of time in the median access for the storage when we do data-intensive applications, and less significant time in the system services code, meaning operating system kernels and so on. In the past 20 years, what happened was that companies like NVIDIA, AMD, accelerated applications basically just eat up, just squash all the execution time for a lot of these applications. The median world made huge progress in terms of NVMe, in terms of SSDs, and the median access time also got squashed. But the system service time has not improved. Even in the CPU world, the system service time has not even adopted the SIMD instructions significantly for exception reasons and so on. I would like to see the computer architecture community to take away that divide and start to accelerate all the services and introduce much more parallelism into the median access. So this is what we call the data as accelerated service vision. And so we are building these privileged and user mode applications in the cloud computing world so that we can move all the performance critical service routines into the GPU acceleration world or other acceleration world. So I'm going to leave the details of this explanation to David Wood, who gave plenty of lectures on Little's law. But I want to just tell you that in order for us to tolerate enough of the storage latency and access data in a precise way, not bring the bulk of data into the memory and then try to figure things out, for a Gen 4 SSD supporting Ampere, we will need to have about 15,000 simultaneous accesses, 512 bytes each, in order to saturate the input bandwidth. And that's a theoretical limit. What we are constantly seeing today is that we're not using even the we're not even using the 25 gigabyte per second for Gen 4. We're seeing about 1 gigabyte for most of the data-intensive applications. This is what I mean by multiple orders of magnitude off from the theoretical limit. So since 2016, we have built BAM and we open sourced it, and a lot of our partners are now using BAM for new SSD controller design in the network, the NIC design and switch design, so that we can achieve the level of transfers and so on. So what is the vision? The vision is we would like to be able to do fine-grained, precise access into petascale data with millisecond level latency and terabyte level throughput. And this, for whatever processor in the middle, is the little thing. The real value is the massive data that we can poke at, we can grab, and we can translate into real value. With that, I'd like to thank all the PhD students and all my postdocs who truly, truly deserve this recognition. And I'm here to represent them to receive this award. These people entrusted me their most formative years. They also allowed me to convince them what is important, and sometimes convince them that doing engineering work rather than writing another ISCA paper is the right thing to do. Many of them disagree with me, but after they graduated, they still choose to be in touch with me. So, I'm eternally grateful. I'd like to thank all the giants who have lent their shoulder so that I can, accelerate the computer systems better. And I'd like to thank all the co-authors who, consider me as a worthy collaborator. And I'd like to circle back to 1984. 1984 is also was the year that I started HPS work, but with Yale. But 1984 is also the year that I met Sabrina, my wife. And so let me set the record straight. Sabrina was a bright, beautiful undergraduate student who was clearly out of my league, okay? And so for some reason, I was able to, to overcome my kind of I would say awkward approach. And over the years, I think what I want to say is she's truly the better half of the family, because she was the one who taught me how to think at a higher level in terms of how I relate to the world, how I relate to other people, and even more importantly, how I relate to our children. She's the one who gave me the sense that not everything is problem solving. And just trying to solve problems all the time does not improve my relationship with my children. And so with that, I'd like to thank you so much for listening to me, and I wish you a very, very successful, exciting rest of the ISCA. Thank you.
I want to invite everyone to join me in this toast for Wen Mei and all the awardees today. So thank you very much. Congratulations.
We're a little over time, but we have time for a couple of questions. Please raise your hand and someone will bring you a microphone.
Matteo, please be easy on me.
Hi, Winmei. Congratulations. Winmei, you are the edge of HPS. After working in architecture for 5 years, you completely moved to compilers. What is your recommendation for people who are graduating? According to, what you have done is completely changed the field, right? What would you advise for somebody graduating?
Mowing, great question. So my advice is don't do what I did. it was really hard. The first 3 years of my assistant professor career was really a postdoc, right? So I got lucky. I had Po-Hwa Chan, who actually followed me from Berkeley. He was an undergraduate researcher that I helped Yale to supervise. And he knows a whole lot more about compilers than I do. And so he really taught me a huge amount of just basic knowledge as I started. If I were going to start all over again, I would have tried to do more of I would try to maybe milk a little bit more of my PhD thesis work, especially the checkpoint repair work that I should have finished more strongly. However, there's no regret. Any other? Thank you, Matteo.
This concludes the award ceremony. Go to the next session. Thank you.